The next stop on our exploration of trig functions are the tangent and cotangent graphs. Having looked at sine and cosine, we're going to take a look at tangent and cotangent now. And if we recall, let's start with the tangent of x. Well, tangent of theta. That if you take some angle theta in any circle that you want, and we look at the ratio of the y-coordinate to the x-coordinate in that circle centered at the origin, any radius that you want. Typically we use a radius of 1 because that's nice and convenient, but any circle you look at, the ratio of y to x will give you the tangent of theta. So what we want to do is we want to create a graph of theta versus y equals tangent theta. And so let's see what we get when we start off some values here. If we start with a 0-degree angle or a 0-radian angle, our angle that we would be looking at is right down the y-axis. At that particular point, I know that the x-coordinate is 1 and the y-coordinate is 0, and 0 divided by 1 is 0. So our tangent graph is going to start at 0, 0. Near there, if we go a little bit larger, we're going to have a small y value and an x value that's maybe a little bit smaller than 1, but larger than that. And so we're going to get a little bit steeper value over here, a little bit higher value, a little bit value above the x-axis. That's going to continue until we get to pi over 4. Something nice happens at pi over 4. At pi over 4, our y value is going to be 1 there at pi over 4, right? Because at a 45-degree angle, at a angle of pi over 4, I know at that we know that we were going to an isosceles triangle. The two angles that aren't the right angle are going to be both 45 degrees. Y is going to be equal to x, and so the ratio of y over x will equal 1. And actually, as we think about it a little bit there, if you look at whatever ray that you're drawing out here, you can also look at it in terms of the slope. That if you look at the rise over the run, well, to get from the origin out to that particular point, you're going to travel up a distance of y and over a distance of x. So the slope of this line is actually also equal to the tangent of theta. In there is the slope of that line. And so as we start close to 0, our slope would be close to 0. And as theta, as the angle gets closer to, what happens is we get closer and closer to 90, our slope just keeps getting larger and larger and larger. And at pi over 2, or 90 degrees, we end up with a vertical line. It has an undefined slope. The coordinates of the point there, right on the y-axis, where a circle intersects, of a circle of radius 1, would be x-coordinate is 0, y-coordinate is 1. And so if you're trying to find the tangent, you'd be taking 1 and trying to divide by 0. And we can't divide by 0. Division by 0 is undefined. But as you get closer and closer and closer to that, you get a very large, steep number. So our slope keeps getting larger and larger, and we end up with a vertical asymptote at pi over 2. All right, if I go just past pi over 2, if I go to an angle in the second quadrant here, what I end up with is also a very large in size, but negative number. I'll have a negative downward trend, so I'm going to have a very large negative downward trend. At 3 pi over 4, our reference angle turns to that 45-degree angle at right at 45 degrees. We'll get back to the point where our x-coordinate and y-coordinate are the same thing. Same value there, right at 45 degrees. And so we'll get a slope there of -1. And then when we get back down over here to pi, the tangent will be back to being 0 again. All right, so it comes in here, actually curves in this direction here. It's concave down through that whole sequence there. At pi, we get 0, And then we're going to get small positive slopes as we come up past that 0. So we're going to come up past that 0 until I get to that another nice, should be 5 pi over 4, where I get a y coordinate of 1. So it's going to increase to 1. At 3 pi over 2, I hit another asymptote at when I come all the way around, and so that I'm looking at the, what's going on here? Draw, please. At the heading down the negative y-axis there, if that's my terminal angle. At 3 pi over 2, I get a vertical line. I'm trying to divide by 0, and I get steeper and steeper and steeper, but a positive slope going through that area. So it heads off to infinity there. Uh, and and then once I get past that little pi over 2, I get a very steep, very negative slope again. It's going to come back up. If I go through all the way to 2 pi, I'll come back up. So once around the circle, we'll get this sort of graph shape to us. And if we were to go the opposite direction, if we're going to the negative direction, if I come a little in the negative direction, I'm going to get negative slopes as we go here. At minus pi over 4, the y value is 1, and so I get a graph that goes like this. And at negative pi over 2, I'm going to have that asymptote again. So our tangent curve is the series of it's sort of roughly resembles the a cubic function. If you remember, y equals x cubed has this sort of shouldery shape to it, but the y equals x cubed doesn't repeat, and it doesn't have asymptotes, but it's got a very similar uh, sort of shape in general, roughly, that you're looking at there for our tangent function that we're looking at in there. Of note, for our tangent function, we don't necessarily have what we refer to some of the characteristics we had for sine and cosine or periodic functions. There is a period. That's something to note. The period in this case, the time it takes to repeat itself, isn't 2 pi. It's certainly repeating over here at 2 pi. You got that same shape happening at 2 pi, but it actually starts to repeat after just pi. So kind of different from the sine and cosine, where the period was 2 pi. The period for the tangent function is 180 degrees or pi, if we're counting things in radians. We also don't really have an amplitude. In this case, because there's no upper value. The range that we're looking at here for the tangent function goes from negative infinity to positive infinity. So it keeps starting down here at negative infinity at the lowest point. Highest point is positive infinity. There is no lowest point. There is no highest point in there. So there's not really a amplitude to talk about in here, but a lot of times we'll look at this 45-degree as sort of a reference thing. At 45 degrees, I know that the tangent value is 1, which is a nice kind of reference point to look at in there. In terms of if you're looking for some sort of vertical stretch. Actually, let's go and look at that. Let me switch over here to Desmos. And here's Desmos's graph of the tangent function. I've got it here showing in blue is the basic tangent function. And I've got it measuring in radians. If we check the settings, you'll see my settings. My angle is in radian mode down here. So we've got a period here, a little bit past 3. We're at 3.14, just a period here of pi to go through one cycle of our graph in there. Let me make this so you see the whole thing. Well, and then here at minus pi, we've gone through that sort of that whole sequence in there. At pi over 4, which is where I've drawn this dot, that's at pi over 4, and the y value at that point is 1 in there. We have asymptotes at pi over 2, and 3 pi over 2, or pi over 2 and 3 pi over 2. Yeah, way over here is 3 pi over 2. 0 is at 0, and pi. Tangent has a period of pi in there. Um, bring these things back. If you change the a value, so if I put an a in front of tangent, if I make a positive, the graph is actually being stretched vertically. If I move a to a value of 2, really the place to look there is at 1. I know that the y value is, well, here it's 1.8. I'm not quite to 2, but I can move it to 2. They're right at 2. This point's going to be right at 2. So if we use that pi over 4 as sort of a reference point, it's normally 1. But if you shift a to 2, or if you shift a to 3 at pi over 4, the y value slides up to whatever value that is. The x-intercepts stay the same. The x-intercepts are exactly the same spot. As you change what the a value is, it's just a vertical stretch of that graph. Kind of changes a little bit, changes the shape as you do that. All right. If we play around with, oops, 0.3, I want it to be 1. Let's put it back to 1. If we play around with D, D is a vertical shift on that graph, shifts that midline up or down, although there isn't really a midline per se like we have in the sine and the cosine, but it is shifting that sort of horizontal shift up or down based on what D is. And whatever D is, like here, D is equal to 3. So this x-intercept that was at 0 is now at 3. At 45 degrees, instead of being at 1, I'm at 4. At minus 45 degrees, minus pi over 2 would be something, should be here. The y value was originally -1, but now our y value would be at 2 if I shift that up a total of 3 units. So D is a vertical shift. B, like we had with the sine and cosine, the value of B is going to be a horizontal compression. The y-intercept here stays the same, and it goes kind of the opposite. As B gets bigger than 1, the graph actually gets compressed closer into the x-axis. We see more and more periods because we're squeezing the graph in towards the x-axis as B gets bigger here. As B gets bigger, we get more and more periods. At 0, well, we don't have a graph when b is equal to 0. If you go to a negative value, it's actually reflected over the x-axis. There's -1. It's reflected over the x-axis, over the y-axis, sorry. Reflected over the y-axis there when we go to -1. So go down towards 0, it sort of flattens out. And then if I go negative, it reflects over the y-axis. With the a value, as a gets smaller, it's going to bring it down closer to 0 here. And then when a turns negative, it reflects over the x-axis in that one. If we look at that dot, it's moving to the other side of the x-axis. It's reflecting over the x-axis. It is a little bit hard to tell because the tangent function is what we'd call an odd function. It's symmetric about the origin. And so most of the time, a reflection over the x-axis, and we'll give you the same thing as if you reflect over the y-axis there as well. So if you reflect over the x-axis, and you can also reflect over the y-axis and give it the same. Well, if I do both of them, let's see, it was the b value. If I made the b value -1, I'm almost back to the exact same graph again. I've reflected it over both the x-axis and the y-axis, and I end up at the same thing. Of course, so my point has moved from the first quadrant down here to the fourth quadrant. Is flipped over the x-axis and over the y-axis, but the symmetry of the tangent graph kind of puts you back right on that same graph as you would. D is a vertical shift up or down. C is a horizontal shift left to right there. And if I make these both positive 1 here, A and B, A and B both positive 1, you can really see that horizontal shift with C. Whoops, I don't want to. There, let me play with my C value. It's a horizontal shift there. And if you move C in the positive direction, the graph actually shifts in the negative. And if you move C in the negative direction, the graph shifts to the positive side. So that's kind of a backwards thing in there. You should notice that, I don't know if you've caught on, these are the exact same transformations that we studied in Math 151, and the parameters do the exact same things. That if you've got that inside uh, uh, thing going on there, the B and the C are a horizontal shift, are moving things horizontally. And the inside thing is actually kind of doing the opposite of what you'd expect it to. If you make B equal to 2, it doesn't, it compresses by a factor of 2. The Y value here, so this value here is exactly, if you're looking at the um, distance from the x-axis. So this is the one where it's 2, where B is 2, and here is B is 1. If you look at the distance here, it's actually cut the distance from the origin out to that point horizontally in half when B is equal to 2. And the bigger you make B, the more compressed horizontally it gets there. Um, and C is a, let me get back to my other tool, and then C is a horizontal shift here. And if you move it in the positive direction, the graph actually shifts in the negative direction. And if you move it in the negative direction, the graph shifts in the positive. C is a negative number. It actually shifts to the right, kind of shifts the opposite direction in there. Those inside things kind of do the opposite of what you expect. The outside values, the A, if you make A larger, it makes the graph stretch vertically. If you make it 2, where's 2 there? There's 2. Looks like make B back to 1 here. Changing too many things at once. So here, if you look vertically, your heights are doubled here. So that your vertical distance here versus your vertical distance there, it's doubled vertically away from the x-axis there. When A is equal to 2, it's twice as high as it used to be. And if I make A 3, it should be 3 units, it'd be 3 times as high. Anywhere you'd go, if you compare the original, let's go down in here, we can look at things. If you pick some X value and you look at how high this is versus how high our new graph is, when A is equal to 3, it's actually 3 times the height here. So here our X value was about 1, well, about one of these marks. I think that's about a half. And so this is about well, it's about a half, about 1.5 there to get to that part. It's 3 times the size that it was initially. That happens here at 1. And if I compare that with, if I take and look at the distance from the top, from the red graph all the way down to the x-axis, it's actually 3 of those lengths long in there when A is equal to 3. It's 3 times taller when A is equal to 3. And so the A and the D shift, the outside shift, does exactly what it expects to do, and the inside shift does the opposite in there. So that's the tangent graph. Let's go back and talk a little bit about the cotangent graph. Let's see, I want to make that go away. All right, and then shift over to my other program here. If we look at the cotangent graph, the cotangent is the reciprocal of the tangent. So if I graph the cotangent, what happens is, if I go back to my circle over here, and we'll make it a unit circle, a circle of radius 1. And so this is like 0, 1, and this is 1, 0. If you look at 0 degrees, you get that the cotangent of theta, 0 radians or 0 degrees, it's going to be 1 divided by 0. It's undefined here at 0, 0. And at pi over 2, at pi over 2 is when I get a value of 0. At pi over 2, cotangent, again, is the x-coordinate divided by the y-coordinate. And so uh, at pi over 2, I'm looking at 0 divided by 1, and my cotangent function is equal to 0. And so what I end up with, and then at pi, I get another asymptote. It's undefined at that point. And then at 3 pi over 2, it's equal to 0. And then at 2 pi, it's undefined again for the cosine, or the cotangent, sorry, cotangent here. And I get a graph, very similar shape. It almost looks like it's been reflected over and then shifted over some. There is kind of a reflection and a shift going on in there. But the cotangent graph looks kind of similar to the tangent graph, with a reflection and a shift going on in there. The period is still pi. Period for tangent and cotangent is pi. The range is minus infinity to infinity. Let's talk about the domain, maybe the domain. The domain of tangent, well, let's put it up here. Here's the domain of tangent. Is all numbers except pi over 2 plus pi k. So at 90 degrees, any multiple of that with add 180 degrees to that, or add pi to that. So when you're looking straight up and down on the y-axis, or if you add pi to that or add another pi to it, it's going to take you back to where you were. Pi over 2, 3 pi over 2, 3 pi over 2 is there. 5 pi over 2, those are all places where the tangent is undefined, but any other place it exists. For the cotangent, it would be 0 plus pi k, or just pi k. At 0 degrees, pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, minus 2 pi, minus 3 pi. It's going to be undefined. So it's all real numbers except 0 plus 2 pi k. And I have that written next to the tangent, and it's not the tangent, it is the cotangent, where that is the domain of cotangent of theta is all real numbers except 0 plus pi k in there. Okay, it can be a little bit more challenging to identify a graph of those, and we can check on Desmos as well. Where's there's my Desmos graph. Whoops, it appeared and then it disappeared. There we are. Got click happy. If I change this, let's go back to the standard of A being 1. There we are. And D equals 0. So our default tangent graph, if I change my function to a cotangent, cotangent. Whoops. I got V, not C. C-O-T. So there's our cotangent graph. So it has that same similar graph that you see with the tangent function, but the asymptotes are in different spots. Instead of being here at pi over 2, I've got a 0 at pi over 2 instead, where the tangent is 0. the cotangent is pi over 2. The graphs do intersect when x is equal to 1 at pi over 4, at 3 pi over 4, at well, pi over 4, and every pi, and 3 pi over 4, and every 45 degrees, right? Uh, was it every 45 degrees? Yes, every 45 degrees, there that every pi over 4, um, you're going to get uh, the x and the y coordinate being the same value. And so you're going to get either 1 or potentially -1 when one of the two is negative. You're going to get a negative value out there. So very similar kinds of things there. Okay, so here we have the graph of a function, and we're trying to come up with its equation. And so we want to look at a couple of things. If I use just the starting value, here it looks like we've got a nice graph that's going through the origin. And so let's go ahead and assume that we're looking at a tangent graph, that this is roughly like a tangent graph. And so I want a tangent of x, and actually I just maybe need a bx in this one. It looks like that we're roughly symmetrical on either side of that point. If you go to a negative value and a positive value, here we're +2 and -2. We're the same distance on either side of that origin. I don't think this graph has been shifted horizontally really at all, or shifted vertically at all. So I think we're okay if if I go here to 4 and -4, it appears that we're the same distance on either side. Y value horizontally, we're the same distance. So I don't think there's any sort of vertical shift, or also in the sort of the center of that curve. So I don't think there's any sort of shift up or down as well based on this graph. You want to look at kind of things like that for this thing. So let's look at the period. Let's look at the period of that. It appears that our graph is repeating every 2 units. So it appears like the period is equal to 2. And I know that there's a relationship between b and the period. For sine and cosine, it's 2 pi divided by b gives you the period. But because the tangent has a period of pi, I know that pi divided by b has to equal the period. So pi divided by b has to equal 2. And so pi is equal to 2b. And so my b value that I'm looking at is pi divided by 2. So that's a piece of my formula that I know I'm looking at. I know I'm looking at y equals something times the tangent of pi over 2 times b, or times times x in there, not times b. Eraser. Pen. Okay. Pi over 2 times x. And then the next thing left to look at is that what is that a value that we're looking at? What's the a value associated with our things? And the key is to look at pi over 4, that 45 degree, kind of find the equivalent of that 45 degree value in here. So I know my period is going to be 2, and so half the period would be 1, and halfway through the tangents period, you have a asymptote. And then so the next thing I want to look at is a quarter of the way through. So if I take that distance period and I divide it in half, let's see, I've got 5. This would be in the middle of this one here. That's sort of the quarter of a period mark. That's the pi over 4 sort of spot. And so I want to look at what's my y value there at a quarter of the way through the period. If I go back, let me jump over here to the tangent graph. Do I still have yep, there's the tangent. Ooh, all my drawings came with me. But if you look at the tangent of graph, that pi over 4 was 1/4 of the distance through the whole period. That's pretty messy. Let me go back to this one. But that's where that value is, and it looks like I've got a value of 3, so I've been stretched vertically by a factor of 3 there. So it looks like I've got a vertical stretch of 3 because that's what my at a quarter of the way through the period I'm up at 3, and 3/4 of the way through the period, which would be halfway here, my y value appears to be -3 coming across there, which is consistent with that at 3 and at -3 would kind of hint that my a value here should be a 3. So I think this equation is y equals 3 tangent of pi over 2 times x would be that equation in there. And I can always go and show you the formula over here. Let me get that. I've got a menu right over the top of it. And so if I show my formula that I worked with, sure enough, it's y equals 3 times the tangent of pi over 2 in there. So if you're trying to find the equation from a graph, those are the things you want to look for. The period for a tangent curve is pi over b. So I know, look at the graph, identify what the period is, and then pi over b has got to equal that period, and that gives you something you can solve to find the b value. And then look for that 1/4 of the way through the period. Look for 1/4 of the way in. That will tell you what the a value is in there. That's kind of the amplitude. It's not really an amplitude because the tangent doesn't have an amplitude, but that's the thing to look for to help find that equation. Okay. Cotangent behaves just like the tangent in terms of period and vertical stretches. Everything happens there the same. It's just that uh, it's a little bit different shape to it. It starts high and curves down with an asymptote right along the x-axis in there. Most of the time we can get by with reflecting a tangent curve instead of using a cotangent, but sometimes using a cotangent is easier so you don't have to deal with any sort of horizontal shift. Okay, so there is the tangent graph and the cotangent graph. Let's come back over to this one, and maybe I'll erase all my scratch work there so we'll look at them again. Clear my drawings. There we are. All right, so there's your tangent graph and your cotangent graph. The tangent graph in blue, the cotangent graph in red.